Good morning, class. Again, today is September
Good morning.
29th. Thank you, Sasha. Today is the 29th. We have important, basically, topics that we need to cover. They are actually going to be part of exam 2. So I really need everybody's attention. I know we have quite a few people who are not here today. And this is typical, basically, of how semesters usually progress. We have a lot of attendance in the beginning of the semester. Usually, attendance starts to drop down a little later, especially since we are not doing this, since we're doing it online. Granted that this stuff is recorded, and I'm hoping that everybody else who is not in here because they are tied up with work or something else, that they're going to follow this recording later on because it's graded. Okay, it's graded in a sense that you still have to watch it regardless whether you do it live or not, because of the fact that there are prompts that follow where you need to answer those prompts, and that's part of your overall grade. So that's one thing. The other thing also that I noticed throughout the years is that people around exams come back and start to focus more on getting those things done. So we still have another exam that is coming very soon. So that's important. So we really have to get ready for that. And then that's basically how normal things progress in terms of these things. Okay. So chapter, forgot the number right now, but it's chapter 10 today. Okay. So let me share the screen with you guys. Again, it's all about waves and sound, okay? More specifically about sound, but sound is a special case of waves. So we're going to be talking, this is what the chapter is about. So let's talk about the points of this chapter. We're going to talk about something that sometimes may be confusing a little bit if you're not too familiar with these things, and this the difference between vibrations and waves. And from the get-go, I'm going to state the fact that the difference has to do with the spatial behavior in space. One of them travels in space. Okay, I need my, yeah, I have it. One of them travels in space. The other one does not travel in space. The other one stays in its place. So that's the difference. The difference is space, which brings me to prompt number 1. The difference between vibrations and waves is the one of them travels in space, the other one does not. Namely, waves travel in space, vibrations do not. Sometimes vibrations they are referred to as oscillations. Okay, that's behavior that is only in time, whereas waves they both spread in space and also they have a temporal behavior. So they are time plus space. So that's the biggest difference. And so this is question number 1 for the discussion later on. Okay. I want everybody from the get-go to make that distinction, the difference between the two. Okay. Talk about wave motion. You will see actually that what travels actually is not something tangible. It's not like mass that is traveling. Waves, what travels in this case is actually the energy carried by the wave. So it's a disturbance really. So this is a disturbance that happens only in a localized place. So for example, let me get my slinky in here. I have a slinky in here. So if I have a mass attached to it, that mass can go up and down, up and down, up and down, but doesn't travel anywhere in space. I mean, yes, it goes up and down in space, but that's a localized behavior only in this local area. Whereas, for example, the same slinky can have a wave that travels from one end of the slinky to the other. And this is the difference between them. So if I create a disturbance on one end, it's going to travel to the other end. So that's the difference between them. And there are two kinds of disturbances that I could create with the slinky. This is another one. Both of them, I grabbed them from a store near Chicago when I was visiting a few years back. Okay. So this is, you can find them in any store. I think the teacher store has a lot of these things. Okay. Example, for example, of a wave that travels in space is sound. Okay, sound is coming from my basically the different compression and ratification that is produced by the motion of my lips and tongues and all of that. So that produces that disturbance. That travels all the way. It's actually only here on the microphone. I'm sorry. Then it carried through a signal, electronic signal, travels through space, and then comes back to your computer. Okay. And at that point, it emerges from the speakers of your computer all the way to where you're listening, or if you have a headset like mine, again, it travels electronically, and then the headset produces the vibrations, basically, of in space that gets in the ear, and then it's going to travel into a drum. This is basically how we're doing it nowadays. But if we are, for example, in a classroom environment, or if you happen to be in a some sort of a concert or something like that, or in open space when somebody is talking, there is no electronic interpreters between you and the person who's talking. So in that case, the person or the source of the sound in general. So in this case, travels through space, travels through air. Okay. There is another kind of wave, for example, that we can mention in this case, which is light. Light also is a wave, and that does not require a medium at all to travel. That travels in empty space. Case in point, the light that we have outside this morning is coming from the sun. It left the sun about 8 minutes ago and arrived to us. There is nothing between the earth and the sun. There is empty space, basically, and traveled through it and made it. The stars, for example, sometimes take thousands of years, sometimes hundreds of years for light to be received from them, sometimes from galaxies, even millions of years or even more for light to arrive from those sources. So again, it travels through empty space. So that is the same disturbance that was created, for example, inside the core of the star. For certain nuclear reactions, that disturbance create transition in the electrons that emits a specific frequency. That frequency now leaves the core of the sun, travels all the way to up to the surface of the sun, and now is ejected from the sun and takes about 8 minutes to come to us, to arrive to us. Okay, so that's basically in the case of light. The case of sound, it's a different mechanism. It involves mechanical motion. And disturbance on a slinky involves mechanical motion also. And there are all kinds of, for example, on the surface of the water, you can create a disturbance on the surface of the water. And you notice that that disturbance travels actually in a spherical, circular patterns, okay? And it goes all the way throughout the entire pond, at least on the surface. Inside the water, the same disturbance could create propagation in 3D, basically making that same surface more like a spherical shape if the water is calm and the pressure is uniform and the temperature is the same throughout the water. Okay, otherwise it's going to see different media, is going to have all kinds of phenomenon, and those phenomenon have to do with sometimes this kind of behavior. Sometimes the waves, when it hits another surface, it reflects. Sometimes it doesn't reflect but breaks down because it goes through different densities in media. It refracts, okay? And this is true for all waves, okay? Well, whether it's sound, whether it's optical waves, like, for example, light, whether it's any kind of disturbance, the minute it hits a different medium, that's what happens to it. On a string, for example, you take a string and you build tension in it, okay? And it creates a disturbance. That disturbance travels from one end to the other, okay? And that's how musical instruments are actually formed, with kind of strings that produce specific frequencies. Now, when it hits one end to the other, it's actually going to bounce back. That's reflected, okay? Sometimes if you create two strings, one with different thickness than the other, or a different properties, actually different density than the other, and you attach them together and you connect from one end and you create a disturbance on one end, that disturbance, when it reaches the point where the two types of strings connect, it's going to change basically behavior and continue to the other side. That is actually refracted, kind of refraction, because it went through different media, okay? So those are the behavior of waves when it hits different media. There are two kinds of essential waves, okay? There are actually in practice a little bit more, but they break down into two kinds of behaviors. There is a so-called transverse wave and the so-called longitudinal wave. Those are the two kinds of behaviors. Now, since the wave is a disturbance that travels, it has two possibilities. Here is disturbance that I created in here. It could travel in this direction. So in which case in here, that disturbance is perpendicular to the direction of travel. In other words, it's going up and down, perpendicular to which way it's moving. I call this kind of disturbance transverse. Transverse means normal, means perpendicular. They are making a 90-degree angle. So this is a behavior of a transverse wave. Okay. Versus, if I take the slinky, for example, I have the slinky in here. What I do in this case, I come to this region and compress it. So what happened in this case, the slinky would look like this, compressed and then relaxed. Okay. This disturbance will travel along the slinky, but this compression would travel also along the slinky. This is called longitudinal wave or sometimes compressional wave. It's similar. Okay. If you have ever experienced an earthquake, you would see that there are two kinds of motions. I was sleeping once and I felt it. I was sleeping actually on the floor. It was, I don't remember where. It was actually in the living room somewhere else. But the thing with it is, I was sleeping and then I felt something was pulled underneath of me. And then later on, the other behavior came in. So in this case, you have the so-called P wave and the S wave, okay? So that's the same thing, but they travel at different rates. So that's the same thing in here with transverse and longitudinal waves. So earthquakes, seismic waves, which are also waves, they also, they come at least in two forms, the S wave and the P wave. And that's what you hear the people, the weathermen talking about when they're talking about earthquakes or scientists and things like that. That's basically the difference between them. So then we'll talk more specifically about sound waves, okay? Again, sound waves in here, the context of it is really an example, but it has some applications, at least for us, that may be of interest to us down the road, which is musical instruments, musical sound, and the difference between normal sound, between a noise, and between a musical sound, which has this kind of repetition in it with specific frequencies that tend to repeat. We talk about resonance, which is an important phenomenon that we deal with on a regular basis. The biggest example is the Tacoma Bridge that was built, and the engineers who built it, they did not do the calculations correctly in a sense that the proper frequency of the bridge was very close from the wind, basically, frequencies. And when these two are very close, and now when the wind blows, it forces the bridge to oscillate, okay? So in this case, the bridge starts to oscillate, and because it's synchronized oscillation with the source of the vibrations, namely the wind, so in this case, the motion is amplified, and each next oscillation will have a higher and higher amplitude. The bridge actually fell because those oscillations became so violent, and the bridge fell. So that's an example of resonance that happened. But if again, you can watch it probably on YouTube with those ladies, singers who have very high frequency and they cause the glass to break, okay? But of course, we use it for other applications. It has a lot of applications. One of the things, for example, is sending a signal, especially receiving a signal. You have stations, for example, that broadcast in all kinds of signals. Here in Southern California, you have almost radio stations everywhere, and TV stations, and phone signals, and all kinds of things. They broadcast in all kinds of frequencies. And if you are a broadcaster, for example, if you want to listen to a specific station, if you want to have your phone working specifically with a specific carrier, that phone or that device needs to be synchronized, need to have its own frequency in sync with the source. So what you do in this case, at least with the old dial tones, you change the internal frequency of the receiver to match that of the sender, in which case the signal will be the highest, which is easily amplified, and then you can watch or listen or do whatever you want to do with that signal. So it's used extensively in telecommunications, the phenomenon of resonance. It's also used in medical diagnosis, for example, trying to identify specific elements in a compound or trying to analyze the structure based on its properties. So again, you send signals, and based on the response, if those signals they come in sync with the vibrations of whatever you're looking for, whether, for example, tumors or bones or whatever that is. So again, that is the purpose of it. And you will notice in all of this device they have the word R in it, and at the end stands for resonance. Okay. So this is used a lot. Used a lot in science, used a lot in technology, and as engineers, have to be very careful when you build a building to make sure its natural frequencies are not within the range of any kind of exciting force that might bring them into resonance, in which case they will be under a lot of stress, which can cause their collapse. And this is true for buildings, true for cars also. Car on the road, for example, might hit a specific disturbance on the road, for example, that can cause it to oscillate violently, and that causes it to also start to break down. So it's true everywhere, okay? So you have to be very careful with this phenomenon. It's a very important phenomenon to understand and study, okay? Well, then we talk about the interference. Interference is when two waves. This is unique to waves. Okay, interference cannot be done with anything else. For example, if you throw a ball on the wall, it's going to refract. It's going to reflect. Just like, for example, you throw a wave on the wall, is going to reflect. Sound reflects off the walls. So reflection is not really unique to waves. So if you see something reflecting, it might indicate that it's made out of particles, tiny particles, okay? And you might even have an explanation for refraction based on particular structure. But for interference, this is only unique to waves. For example, if you create two disturbances on the surface of the water, you throw two rocks. One rock will create circular patterns. The other one will create circular patterns. When they meet, when the two circular patterns start to meet, they entangle with one another. There are two possibilities, or three, if you want to call the stage in between. If the peak of one wave corresponds with the peak of the second wave, let me get another color in here. So you have two waves, and both of them have the same peaks in sync, then the resulting wave will be very strong, okay? So it will double basically in size. So in this case, this is called constructive interference. They add up. If, on the other hand, a wave comes up opposite to another one, both of them have the same amplitude but different phases, then in this case, the resulting wave will be cancellation. So this is called destructive wave. The problem with this one is there are behavior in between them. If one of them is still peak, the other one is still somewhat the same peak, of course, they have the same magnitude. The resulting wave could be anywhere in between them. This cannot be true, for example, for particles. If I have one particle and another particle and put them one next to one another, I can still clear two particles. I cannot see them fuse into a bigger one. This is true for waves. If somehow they are out of phase, I will see 1.5 particle or 2.5, 1 3/4 particle or 0.7 particle. It doesn't make sense, okay? Or if you have two particles, no matter which way I bring them, it cannot cancel each other, at least if they're still particles. So this behavior is unique to waves. And the reason why I'm saying that is that because when people saw that particles exhibit this behavior, that was revolutionary. So basically, that's the advent of a new physics that was quantum mechanics, because it relied on this idea. In order for us to understand, for example, how the atom is structured, we really have to have, in addition to the fact that an electron, for example, is a particle with specific mass, a specific charge, it's also a wave. So this is really a revolutionary approach to dealing with science, that the same thing can be a wave and a particle at the same time. So that was something that, and this can be for any particles, not just the electrons, which means that for any combination of this, they can exhibit the same behavior, which means that even on the macroscopic level, objects on the big size level, they have this behavior. So again, this is unique to waves. If you see it, you know you're dealing with wave. So this is the signature of a wave. So if you see it, that's its stamp. So if you see an interference, you know you're dealing with a wave, okay? That's it. That's basically its mark. Nobody else can do that, okay? Then we talk about the Doppler effect, which is, again, behavior for waves. You have three things at play in here. You have a wave source, something that produces a wave. Like, for example, an ambulance, okay? Going on the road. So an ambulance by itself, for example, if it's sitting still, that's fine. It's producing sound. The person has the siren on, that's fine. And then another thing in here, you have the, so you have a source, you have the wave itself, which is in this case the sound, okay? And you need an observer. You need the third thing in here, somebody to collect that wave, to listen to that wave, or to study that wave, or to capture that wave. So you need three things for Doppler effect. You need the source, you need an observer, and you need the wave. You need three things. Now, the source could be stationary or moving. That's one thing. The wave is, of course, moving. That's because part of the properties of wave travels in space. And then you have the observer, which could be stationary or moving. Here are the possibilities. Either the resultant of the motion of the source and the observer is they're getting closer. The result of this is that the frequency, the pitch tend toward higher values, okay? And even if you close your eyes and the ambulance is coming toward you, whether you're moving or stationary, you can tell. You can tell the fire department is approaching or receding from you just by the relative motion between you and the other source. The police officer, you can tell if he's approaching or receding. That is the result of this. So if they're approaching, the pitch is higher. If they're receding, the pitch is lower. Okay? Even if you have your eyes completely blindfolded and you don't know where the source is coming from, just by listening at the pitch, the sound, you can tell. Is he or is she approaching or not? Just by basically listening to the pitch, the frequency. Is it getting toward higher and higher frequencies? Then you know, even though probably you're moving away, that they are coming faster towards you. Okay? Or if the frequency is getting toward lower and lower values, your ear will tell you that, hey, this source is, you are moving faster. You're moving away. Okay? So that's basically the point in here. So this is the Doppler effect. Again, it plays a major role in science and technology. Again, it's used by police, for example, officers in their radar technology to detect how fast you're moving. That's one thing. Okay? So they use that. It's also used, for example, in science extensively in terms of determining the motion of objects. For example, how fast is the star, for example, is spinning around this axis, if we can determine that, if there is a shift. The problem with that is the frequency will shift toward higher or lower, but sometimes very small, okay, shift. You cannot really see it. It depends on the measurement. Technically, anytime it's coming towards you, the frequency in this case is higher. Anytime it's receding from you, the frequency is lower. So if you take a star, for example, the sun, which is spinning, one part of it is coming towards you, the other part is moving away from you. So on one side, you should see a higher frequency, namely a shift toward the blue color, whereas on the other side, it's going to be a lower shift, meaning that it's going to be shifted toward the red color. So on one side should be blue, and the other side should be red. Okay. You have seen the picture of the black hole that was published in 2017. Was it the M87 black hole, which was in a big deal in the news because for the first time we were able to capture a picture actually of a black hole. Of course, you are saying, oh, how can we see a black hole when it's captures light? Yes, we cannot if it's not active, but when it's active, feeding basically on different stars or different materials, the materials as they are falling in or into the black hole, they emit radiation. Now, since the black hole is spinning and actually it's turning not just itself, it's turning the entire space around it. So in this case, the material that is falling in has a different color from the other one. If you see the picture, you will see that some parts of the black hole are actually redder than the others and whiter than the others, indicating that the black hole actually is, which is a big object, is spinning. So that could be determined for that. Not only that, but we were able to determine all of the galaxies that are far away from the Earth move away from the Earth, move away from the sun. So it seems like the entire universe is actually expanding. This is how it was determined. It was determined based on this one. Again, we use it in interstellar space a lot. We use it in astronomy a lot to determine how fast objects are moving away or towards us and things like that. We use it again in technology. And then we apply the concept of the Doppler effect toward the sonic boom, because at that point, basically what happened in this case, the source is moving so fast that its speed is almost the speed of sound, in which case it's going to have all of the waves. As it moves, it sends a wave. But before that wave starts to move away from the source, it's going to produce another one, and another one, another one. So there is a pileup of wave fronts in front of the plane, and that is the sound barrier. But if it moves faster, it emits a wavefront, and then before the wavefront, it catches it. So you're going to see the plane zoom by first before you hear it. Okay? So it's not like you hear a plane that is moving so slow and you can tell it's coming. Hey, I can see it coming. And then the sound is coming in here because it's moving so slow. But this one is moving super fast that it's going to basically beat its own sound. So that is the sonic boom, okay? And that was a major problem in terms of aeronautics in the early days, because trying to get planes to move faster, especially military applications, it was a major problem trying to overcome that. But then now we know. This has some applications also in science. If you have had a chance to go to a nuclear reactor, for example, you could see in the tank of the nuclear reactor something called the Cherenkov Effect, which is the radiation coming from the materials inside the nuclear reactor are moving faster than the speed of light. Faster than the speed of light. Of course, you're saying, okay, there is nothing that can travel faster than the speed of light. You're absolutely right. But the particles are inside the water, which means the water is actually slower in water because of the, again, it has to do with this concept, actually, the refraction, okay? That the particles actually move faster than it inside the water, and they are still less than the speed of light in the vacuum. So they didn't violate any law in terms of that you have heard of. But so they are traveling less than the speed of light in vacuum. But relatively speaking, inside the water, inside the tank of the nuclear reactor, you will see the particles actually moving faster than the light inside the water, and you will see this beautiful radiation emanating from it. So it's a good, beautiful sight. I mean, it has other applications, so the not just for example, aeronautics and things like that. So this is, in a nutshell, the entire chapter. Spent half an hour just talking about everything, which is really everything that is to know about the waves. So that's the chapter for you guys. Any questions? No? Okay. So let's continue then. So again, I mentioned the fact that the vibration wiggle in time, whereas the other one, whereas the, oops, Control Z, I didn't mean that. The other one is a wiggle in space and time. Okay, so why is this in the second line? I'm sorry. Yeah. and time that transports energy. So that's really the biggest difference between them. Okay. This one also has an energy involved with it too, but it doesn't transport it. It's in the same place. But this one, energy is actually carried from point to point in space. So that's really the difference between them. And here in the picture, I have a tower that is emitting radiations. And this radiation could be a radio signal that could be coming to your cell phone. And if you look at your cell phone, you will see how many bars. I have a single lousy bar right now. I have very lousy reception where I am right now. Anyway, so that's basically the signal traveling from the tower and getting into your receiver. Okay. Waves are characterized by several properties. Okay. You have in this case in here, you have an oscillation, but that oscillation, if it creates a wave, that wave is going to travel in space. The distance between a peak and a peak is what is called the wavelength. You will find, for example, in some of the literature, the symbol for the wavelength is the Greek letter lambda. Okay. So that's how this is symbolized. So it's a wavelength. It's measured in meters. Okay. Sometimes it's so small that we use centimeters. Sometimes it's even smaller. We will be forced to use the micrometer, like the microwave. Okay. Sometimes it's even smaller than that. For example, for light, we don't use a micrometer. We use a nanometer, which is 10 to the negative 9 meters. And there are even shorter wavelengths than this. The ultraviolet, for example, they're shorter. The X-ray, they're even shorter. And the gamma rays are even shorter than all of the above. Okay, so that's basically how the wave in terms of light are. In terms of sound, they're in a few centimeters. There, probably they can go as much as a millimeters and so on and so forth. Okay. The amplitude is the intensity of the sound. You can have the same person saying the same words with the same wavelength, basically, either softly or screaming at you. Person who screams. Now what has happened in here? Did I touch something? I don't think I did. I'm sorry. Okay. Anyway, so the same sound could have the same wavelength, namely the same characteristics, but could be produced with different amplitudes. Okay. Which means that a signal that travels from the source in here, because it travels in space, its intensity now is spread over bigger and bigger areas, which means that for the same person who's got the same surface receiving the sound will capture less and less of it. That's why if you're closer from the source, usually the intensity is higher. When you are far away from the source, your intensity is lower. That's exactly what I meant by the bars earlier. If you happen to be very close from the tower, you will have all the 4 or 5 bars or however many they are on your phone. If you move away from the source, because the same signal is traveling now over a bigger and bigger area, so your device, which has the same antenna, which has the same stuff, now captures less and less of it because this entire signal now is spread toward bigger and bigger surfaces. So this is how the original signal was on this area, and that's why you get so many bars. Now it's just so entire big sphere. If you put your device in here versus in here, now it's capturing just this portion of this big sphere versus it's capturing this same portion of a smaller sphere. Now, so it has a higher intensity. So that's the intensity for sound. It's the intensity or the amplitude for a wave, how intense it is. That's a characteristic. You need that. And that depends on the wave itself. Now, if we're talking about sound waves, that's the pressure. How much pressure is exerting? Usually it's a very tiny value, but our ears are so sensitive to it that we pick those values, okay? If it's if it's light waves, for example, that's going to be in the intensity of the electric field or the magnetic field that it has associated with it. So you can express that intensity there too. If it's a slinky, that's how much, for example, compression you have produced in here, okay? That is the intensity if you produce so many of them or you produce so little, okay? So it could be a very intense or very less. So again, the intensity now depends on the nature of the wave, or the amplitude depends on the nature of the wave. And the wavelengths is from peak to peak or any similar points. This point, for example, is where the last time the wave was coming from its lowest value and getting higher and higher, okay? Now, I cannot say that this is similar to it because now it's going toward this lower value. So now this is similar to the first one. So it's much easier to remember it from peak to peak or from basically trough to trough than having to remember it from this any 2 points. But it's the same one. It's the same wave. So this is actually so-called harmonic wave because it's a sine or a cosine function, okay? So again, crests and troughs, they are the points of the highest and the lowest points in a wave. That's a characteristic of a wave. So I mentioned already the amplitude and the wavelength. There is another thing that characterizes the wave, and that is the frequency. How often does it go up and down? If you happen to live on this point, okay? All you see as far as you're concerned is you're going down because as the wave comes in, okay, this point starts to, let's say, for example, the wave is traveling this way to the right. Then in this case, you're going to start to go down because this portion now arrives to you, okay? So at some point you'll be here. Then this portion arrives to you, so you'll be lower. And then the next wave will reach you, so it's going to take you up and down. So as far as you're concerned, you're replicating the source, that's all. This is the source, okay? So this is the source that produced all of this thing in here. So as far as you're concerned, you're replicating that behavior. So this is a temporal behavior on any given point. The time it takes you to go up and down is what is called the period, T. So this is the period. And it's measured in seconds. How many seconds does a specific point change from its state to a similar state in the future? If it was a max value, when would it become max again? If it was a min value, when would it will be min again? So that's a specific time in second. Now, how many times it goes up and down in 1 second? In 1 second, the number of times, okay, is what is called the frequency. So the frequency and the period are related. The frequency is the inverse of the period. The symbol for frequency, by the way, is F, and the symbol for the period is the time T, capital T, and they are related as such, okay? So that is basically the characteristics. So the wave has several characteristics. It has a wavelength, it has an amplitude, it has a frequency, parentheses, period, because they're related, okay? You can invoke one and the other, they're similar, okay? Period is in seconds. Frequency, if you like, it's 1/seconds. But in honor of Mr. Hertz, who did a lot of work in this area, telecommunications specifically, they give it a name. 1/second is actually given the name of Hertz. And that's what you hear. So many megahertz, so many kilohertz, so many. That's basically the word. Megahertz is so many millions of hertz. That means in 1 second it goes so many times, million times in 1 second. For your phone, it's either most likely it's a 5.5 gigahertz or 2.4 gigahertz, I'm sorry. So in this case, it's going to be 2.4 billion times in 1 second. The oscillation, that is, not the phone, okay? The oscillation that is probably coming to it, okay? And it's regulated by the FCC when it comes to telecommunications in general. So the distance between adjacent peaks and the direction of travel for a transverse wave is it's a distance. It cannot be frequency. I just said the frequency is the inverse of the period. It cannot be the period because that's in seconds, okay? So it has to be a wavelength, and that is the point in here, okay? So the wavelength is the distance between peak and peak. So it's this peak and that peak. It must have gone through a lower point in here. So that is what I call the wavelength. So vibrations, they're described by frequencies. That's actually the source, and it's taken also with the wave too, okay? Now, in addition to the frequency for the wave, in addition to the wavelength, in addition to the amplitude, now we have a characteristic for the wave, which is the speed with which it moves from point to point. That is important because depending, you can have two similar waves with the same amplitude and similar wavelength, but different frequencies. One of them is going up and down. So in this case, one of them will travel faster than the other. As a matter of fact, there is a relationship between the wavelength and the period, and that is what the speed of the wave is. Okay. Remember, 1/period is also frequency. So another way of writing this same expression is then wavelength times frequency. Of course, this is only true for waves, okay? Harmonic waves, that is, okay? This law has a name, they call it the dispersion law, okay? So again, frequency is the number of to and fro vibrations in a given time unit, which is a second. The unit for a frequency is the hertz, okay? And the period is defined the time for it to go back and forth in a single vibration, okay? And the unit for it is a second. So you go up and down. Let's say, for example, this is your starting point. You go up to the max and you come back. The time it takes for you to do that is the period. That's one way of thinking about it. Or take 1 second and count how many times it goes up and down. Okay, that number is the frequency. That's why some number per second. Okay, again, what's going on? Is this from my end, or is this everybody experiencing the same thing?
I thought it was me. I think it's you.
Oh man.
Yeah, because yeah, from like your end, it was crackling, and then like every now and then it would pause for a bit. But then like on my end, it said that I was having some internet connection issues. So I thought like I
Yeah,
was
me
having
too.
the issues at first.
Okay, sorry guys. Okay, so I'll
Everything
probably have, yeah, I'll have to restart the router at some point later today.
everything seems to be working fine right now, at least.
Okay, so let's continue this discussion. Of course, you have the notes for the discussion. I hope you guys can finish it. Remember, we already touched one question of the day, so we still have probably a few more. Let
What
me
was the question? Because it kept lagging.
The question has to do with the difference between a wave and a vibration, and the answer has to do with the spatial behavior. Okay.
Okay.
Okay. Did everybody catch that question? It was in the beginning. Okay. Why now my slides are not working? It has to do with this slide in here. It's all of these things in here, the notes in here. Space and time behavior for waves versus the vibrations, which is just a temporal behavior. I mean, yeah, temporal behavior in time only. Okay. So since this thing is playing games on us, and Zoom is playing games on us, or my internet is playing games on us, one of us is doing that. Earlier, for some reason, it stopped the recording and restarted it by itself, but now the whole thing went up in the smoke. So we're going to expedite this thing quickly, hopefully to catch this whole thing. If it happens again, probably I will finish the recording and I post it on campus. So again, I already mentioned the fact that the frequency and the period, they are related through one another through this expression, okay? Remember, Hertz is just a unit, which is just 1/2. So numerically speaking, it's just the inverse. So for example, to go back to the example of 2.4 times 10 to the power gigahertz, that's 9 Hertz. So if you're curious trying to find the period for that, just take this whole thing and invert it. So 1/10 to the power 9 seconds. Okay, 10 to the power positive 9. So it's going to be 0.2.4. Okay, it's going to be 0. This is about 4. Okay, 4 times 10 to the power -9. So it's going to be 0.000 followed by 0.000, another 0.0, 4 seconds. So that's the signal, how fast it's moving up and down for the electrical signal on your phone, okay? Because it's electrical signal, electrical current that goes up and down. So that's how much time for it takes it to go between maximum value, how many volts per meter, to how many volts per meter in the opposite direction, okay? Now, there is a critical relationship also. Higher frequencies means lower wavelength. Higher frequency means lower wavelength. Lambda, I used the letter lambda earlier. So for example, if I take the gamma rays, which they have very high frequency, which means they also have very high energy, they have very short wavelength. If I take, for example, the visible light, which has actually less frequency, which is less energetic, it doesn't cause as much damage as the X-ray, for example, or the gamma rays, or even the ultraviolet, which are supposed to be very high frequencies, even higher than light. Normal light, anywhere between the violet all the way to the red color, they're actually within a range that doesn't do damage, okay? The wavelengths are very small, okay? Not as small as the X-ray or the gamma ray. The frequencies are very low. They're not as high as the others. But if I take, for example, the microwave region or the infrared, which is actually less than the red, and then you have the microwave, which is even less than the infrared, which is actually kind of infrared, to be honest with you. And then you have the radio waves, which is in longer wavelengths, shorter, longer wavelengths, that means it's lower frequencies. They don't do as much damage at all. So for those people who are creating rumors that somehow this, what is it, the G5 is connected to coronavirus, I have no idea how that works, okay? So the coronavirus itself is much, much, much bigger than those frequencies. So how in the world is going to be related to them? I don't know, okay? I mean, at least in terms of resonance, it doesn't make sense to me. And even there is no science actually behind those rumors. There's a lot of rumors on the internet. Probably you have heard of them, that people are claiming that somehow coronavirus was related to the deployment of the new technology that has to do with a different frequency of basically sending and receiving signals for telecommunications. Did anybody hear about that? Or is it just me? Maybe I'm exposed to too much fake news.
I didn't hear the last part. You said it was due to what, did you say?
That the coronavirus is related to now different phone carriers deploying the new technology, not the what is it, the G4. Now they're using the G5 technology.
Oh, yeah. No, I did hear that.
So I don't think that there is evidence for that, at least in terms of resonance. Yeah.
No, it's the dumbest idea ever.
Okay, I hope you guys know, at least don't think that. Okay, Manuel also heard of the 5G being okay. Okay, Josh, have never heard of such a thing, but now you heard, okay, Josh, so. Okay. Anyway, we have a signal with a frequency of 20 Hertz. That's another point of the discussion. We want to find its period. It's 1/20. Okay. So if I give you the period, the frequency, earlier we took the frequency of the phone. Now we're taking the frequency which is of a normal, some 20 Hertz, which is actually a sound wave, this one, okay? Usually, which is those things that we can hear. then the period in this case is 1/20th of a second, or 0. What is it? This 5, and then you have 0. How many? Is this correct? Probably I'll have to do it to the calculator. Now I'm being so. Yeah. Okay. Seconds. So 5/100ths of a second. If you notice, for example, your signal at home is operating at 60 hertz. That's the light coming at you from the AC current. Okay, 60 hertz. You can do the math. It's 3 times as much as this number. So that's the answer to that question. Again, we talked about the wave speed, and the wave speed describes how fast the disturbance moves throughout the medium. Related to frequency of wavelength. Okay, again. 1 meter over 1 second, or times 1 hertz, it's the same thing, gives you 1 meter per second. So the formula for the speed is V equals to the wavelength. I'm using the letter lambda. If you don't like it, use the letter D, or wavelength, okay, times frequency, or in the same times lambda divided by the period. Okay, so that's the math applications for you guys. Simple. Again, I mentioned already in the beginning that there are 2 kinds of disturbances that I create on the slinky. Either I compress a region and let go of that compression travel throughout the entire medium. So I have compression followed by something called rarefication, followed by another compression, then another rarefication, then another compression, then another rarefication, and then another compression. So my compressions, the rarifications are similar to the crests and the troughs. Okay, that is basically where the maximum amplitude is, and then when the 0 is the equivalent. So when there is still equilibrium, that's equivalent to my rarifications in this case. Okay, so again, this is a longitudinal. The wave is traveling in this direction in either case along the slinky. But the disturbance for the longitudinal or the compressional waves is along the slinky also. Whereas in the transverse is perpendicular to the slinky. That's the difference between the two, okay? Sound is of this type. It's a compressional wave, longitudinal wave. Light is of this type. Okay? Seismic waves are both. Surface waves, which they're on the water, for example, on a pond, they're of this type. The pond goes up and down. So this is the water waves. On the surface, okay? Deep inside the water, it's the other one, okay? It's a compressional wave. So depends on the medium. So again, this should be easy now. The vibrations along transverse wave move in a direction perpendicular to the wave. To be more specific, perpendicular to the wave direction of propagation with which it's moving. Okay, sound, I just mentioned the fact that it's a compressional wave. You exert the air around you is being compressed and relaxed as the wave is moving around it, okay? And it's a disturbance in the air. The number to remember is this one. The sound in air at room temperature, which is 20 degrees Celsius, travels with 340 meters per second. As the temperature changes, it changes with it. It increases with it. It moves faster. That's basically how sound is. It depends on the density of the air too, and the density of the medium. So again, consider a person attending a concert broadcast over a radio signal 45 meters away from the stage. This requires some math because you know the sound is traveling with 340 meters per second and he's sitting at 45 meters. So all you have to do is divide this by that and you will find how long for the time for him to hear the singer, okay? So he's sitting in the opera house and she's singing. So in this case, he's going to listen to the sound with a delay. And like the person who is immediately sitting next to her, he was going to receive the sound closer. Remember, 45 meters is half a football size, so it's a really long size, okay? So there's somebody sitting on the goal post and the other person is midfield, okay? And furthermore, he's got his radio signal on, and if we assume that the signal goes from here, the speaker, to the tower, and the tower broadcasts to where the station is, and the station probably station is, and the station broadcasts to where the satellite is, and the satellite will broadcast the signal back to another station somewhere, to another relay point, and the relay point will send the signal in broadcast points in here on different points in there. Now you have the signal. He's going to receive it on his phone, his device, okay? So actually there is a combination of electronic motion that takes time, okay? Usually super fast, from the microphone to the amplifiers to whatever that thing is, to the signal which compresses it and packages it and send it to the station, which again probably need to do some signal iteration and send it to a satellite and send it to this one. Now it probably has to break it down and then send it with a package. And then now you have, because signal is sent in something called a carrier, now it comes to you with two different signals on his phone. His phone throws the carrier away and takes the signal and transmits it into his ear so that he can see it, can listen to it. Most of the time is traveled here and there, and then there is some electronic motion in there. If you do the calculations for this specific application, you will find that the time are very similar. So he would hear her from one side with the radio, and listen to her with the other ear that is open in the same time, if the numbers happen to be the same thing, okay? And in this specific calculation, we said, okay, it goes around the Earth, so if you do the math, it should arrive at the same time, okay? So that's the question. So the answer to this one, you really need to do calculations to arrive to it, to show that both of them will arrive at the same time, okay? Had he been closer, he probably would hear her first before the signal comes on the radio. Had he been further away, probably he would receive it first on the radio, then he would hear her on the other ear, okay? Again, sound is sent through waves. Now we have a few minutes, we have a little, probably half an hour left, okay? So how sound is heard from, again, we're going to use the speakers in this case. So there is an electronic signal that causes the mechanical motion of the loudspeaker, which then moves in the air, which cuts into the ear, and the ear is a very complicated device. Actually, I didn't know that until I was looking at the schematics for it. So the eardrum starts to move, which this motion is captured by some hair-like structures that goes through the nerve system and goes all the way to the brain, which give you a sensation of a specific frequency depending on how fast the drum is moving back and forth, okay? And now how much it's yanked out of its location and pushed back and pressed back, that is the intensity of sound, okay? Again, the brain has specific values for that. Probably more complicated than the eye, honestly, okay? Again, taking a radio signal, and I already mentioned the fact that it moves, there are some electronic devices, for example, similar to capacitors, and as the capacitor is changing, it's the distance between both ends, its capacitance changes, and then all of a sudden now that transposes into a signal, okay? Because the circuit, when you change one of its components, the signal can be translated into vibrations. For each increase of temperature by 1 degree, speed of sound increases by 0.6. There is a formula for it. So sound in hot air moves faster than sound in cool air. That's basically how you, okay? Reflection, I already mentioned the fact that as the wave bounces off a surface, is going to be reflected. Now it's very critical to remember this law. The angle of incidence is equal to the angle of reflection. So here is a surface that separates basically, that is in the environment. And you have a sound that is coming in here, a wave that is coming in here. This is true for all waves, basically, even for optical waves. And when you when you stand in front of the mirror, it's the reflection of light basically coming from the surface of the mirror. Okay, I hope you guys know that by now, that there is no other you on the other side. Okay, so, and because of this law, the angle of incidence is this one. The angle of reflection is this one. Because they are equal, reflection, there is an image replica of you on the other side, okay? That is sitting on the other side. Everything is similar except left and right are reversed. Everything else is similar. Up and down is the same. Okay, you don't see yourself backward. Okay, so that's because of this law. The angle of reflection equals to the angle of refraction. Okay, so we have quite a few questions today of the day. So we have 1, 2, and this is the third one. Okay. The law of reflection states that the angle of the reflection is equal to the angle of incidence. That's third topic. Okay. If you are keeping tab. And it's true for all of the, now when the surface is rough, you have diffusion actually. Now you have, it's still true for every single point on the surface in here that it's true, but because the surface itself now is jaggedy, so the angle of incidence is different for the next beam. So the beam initially was uniform, now it's going everywhere. So you could say it's send a laser beam on a surface that is rough, provided that the roughness is smaller than the actual cross section of the beam itself, then you're going to scatter it every which way. Which brings me to the law of refraction, okay? If you ever looked at the surface of the water, for example, you will see, for example, the fish in a specific point. Do not attempt to grab it from there, okay? Because your eyes are playing tricks on you. So you think that this beam will extend in here and the fish is here. Whereas actually the fish in here, this is an optical illusion. You try to attempt to go there, but the fish is actually here because the light is coming from the fish, refracted to the surface, and you're standing in here looking at the fish, thinking that the fish is coming, as far as you're concerned, from the other side, and it's not, okay? Again, the angle of incidence is here. The angle of refraction is this one, okay? And they're related in a similar fashion, except that they involve the index of refraction, okay? The index of refraction is the one that determines how much refraction you're going to have, okay? All kinds of interesting phenomena here. Per Mr. Feynman, this is the only experiment known for the Greeks to actually have performed. Okay, the Greeks are known for their thought experiments and philosophy and thinking and so on and so forth, and doing mathematics, which doesn't require experiments. Mr. Feynman recorded the fact that this is the only one that has data in it in their experiments when they recorded this one. Okay. This is just an application of the fact that the speed of light changes. Again, the air is moving faster in the warm side than in here, which is slower. So it tends to bend upward, okay? So your dog will not hear you, okay? On a cool day when the warm is actually. If it's the opposite, now he's going to be alerted to your presence, the fact that you're signaling. Again, the warm is going to move faster than the cool one, and the air bends backward, okay? So this is just an application of the same stuff in there, okay? Other animals use different frequencies for communications that we don't hear when it comes to sound, and sound we are only limited by anywhere between, I think, 20 all the way to 20 kilohertz. That's the maximum we can hear. Something with very, very low frequency, as much as 20 hertz, to very high pitch, which is 20 kilohertz. Some of our hearings, and there are online testers that you can tell whether or not you can hear the frequency or not, depending on how your hearing is. And that degrades with time, actually. As you get older, your hearing range starts to shrink. Okay, that's typical because you lose some of the sensory stuff in your ears. And but for other animals, they can communicate even with higher frequencies, like for example, the bats and dolphins and things like that. Elephants, on the other side, they communicate with even lower frequencies that we don't hear. The place could be very noisy and they could be communicating and we have no idea. And the same thing is true for whales, okay? And low frequencies, they travel even further, a lot further, and that's what allows them to basically listen to one another basically over several hundred, possibly more miles, okay? And we wouldn't even know that they are doing that. Again, I already mentioned the fact that when things are in resonance, they start to produce high intensity in their oscillations. This phenomenon is known as resonance, okay? I have here a tuning fork. Okay, and tuning fork, when you excite it, it's going to produce specific frequency, okay? Again, oops. Very, very low frequency. I mean, the intensity is very low. But the point with this one is it's used, for example, for piano tuning. And it's used a lot extensively in physics because it's produced specific frequency as the two ends of the fork start to move in and out, okay? And producing compressions and ramifications in space that travel in space and produce sounds. So that is one of its applications, okay? And again, it's in resonance when it produces, for example, when you put it on a different chamber, and then it produces different frequencies on the other side. So it could induce frequencies on the other side, which means it forces the other side to move. So you could have forced oscillations due to external agents. Here is the example that I was talking about. This is a Tacoma bridge. While it was oscillating, and because its natural frequency was very close from, was actually equal to that of the wind that was blowing. So in this case, resonance happened and the intensity started to grow. Think of it the following way. If you have a child, for example, on a swing and you're pushing the child at random, and sometimes you hit, sometimes you miss, because sometimes you get the child in, sometimes you try to move and the child is probably somewhere else, or sometimes when you get him, he's already moving, so you don't get as much push. But if you do it in tandem, every time the child is moved back, he's going or she's going to gain more and more speed. So the intensity starts to grow and grow, and sometimes you lose the child in the process. So don't try it, okay? Very dangerous for the child, okay? But the point, this is similar, okay? That's why the intensity increases and the bridge collapsed. So resonance is an important phenomenon. Interference, I already mentioned the fact that this is unique to waves, and waves exhibit this behavior. So each and every one of this is actually disturbance of its own that creates its own waves. But combined, they create specific, unique patterns, okay? There are two kinds of waves, interference. There is constructive interference when they are in phase. When they are out of phase, they're actually completely 180-degree opposite to one another. When the first one is max, the other one is min. When the other one is min, when the first one is min, the second one is max. They will cancel one another. So this type of wave is called constructive interference. The intensity is twice as much. I'm saying the intensity is 4 as much. The amplitude is twice. The intensity is always square of the amplitude. So the amplitude is twice as much. And in here, the amplitude is nothing, is 0. They cancel. But they have to be exactly in this configurations to have these two. If they're anywhere out of these two phases, either they're completely in sync or completely out of phase, then in this case, you will have anywhere stage in between them. Two waves incoming and hitting one another, one coming to the left and one coming to the right, they will interfere against one another, and then they will continue traveling unimpeded as if they did not do that to begin with, okay? And this is true for transverse and compressional waves. It's always the same thing, okay? Interference is a property of all waves, whether sound or light, it doesn't matter what the wave is, okay? That's why you have standing waves on strings. That's why you can do musical, can do music. It's because of this interference phenomenon, okay? And it happens also on strings, so it's not just unique to these two. So again, noise cancellations is one of the problems that you have to deal with, and jammers, for example, for microphones, or even electromagnetic signals for light, for example, is one of the applications. You don't want the enemy to broadcast their propaganda, so you want to do jammers. And this is one way of doing it. For example, if you know the exact amplitude and the frequency of the original signal, then you're going to create a similar amplitude but opposite phase. And then when you put them one next to one another, they will cancel each other completely, and you will be happy because there is no such a thing as what you were trying to have the other one do. Okay. For noise isolations for rooms, for example, they create actually the thickness so that they absorb the sound. They absorb the actual amplitude. Okay, and it's needed for buildings, especially for apartments and rental places and things like that. So you'd want the carpet to have a little bit of absorption, otherwise the neighbors up and down, they will be hearing one another, okay? Again, beats is a different kinds of interference. It's interference still, okay? But when the two frequencies are very close from one another, you will hear a hum, okay? And this is probably also true for your car, okay? Sometimes you hear it humming because they're supposed to have two motions in tandem, but sometimes it doesn't. So you'll hear that humming noise every once in a while, that noise. Or it's usually actually used for example, the piano tuning. When you have a piano that is out of its own frequency, for example, it's supposed to produce this specific note, this specific frequency for that note, and it doesn't. So you bring a tuning fork that produces the same one that you know for sure is working. You produce a sound, and you hit the note, and you see if you hear a hum, that means that the piano needs to be fixed. So you go to the tensioner and you make it even more tense, or you loosen it depending on which way to move. Now, if you still hear the hum and it's getting separated, that means that you're in the right direction. If it's getting there is no such or if it's getting closer, that means you have to go in the opposite direction. There is a fun calculations in here, okay? I met a guy who does that for a living. I didn't know that was really a job. He had actually a business, and he had a website and things like that. Piano tuning. And it's used actually in other applications too, a lot of applications in there. Okay, trying to determine, for example, specific frequency and whether it's not true or not. So you start to tune, and then the minute you're very close from the frequency, then you will start to see those phenomena until the two collapse on one another. Standing waves is one of the case, for example, when you have produce a disturbance, the disturbance hits a medium. In this case, the reflective wave will come again, similar to the first one, except that it has opposite to the first one. And if you produce enough of it, you will see standing waves. Standing wave is characterized by several properties. One of them is the so-called notes. This is a note. Of course, I'm assuming now standing wave has formed in here, okay? I have a node in here, and I have a node in here, and I have an anti-node in the middle. In this case, I have 3 nodes and 2 anti-nodes. In this case, I have 1, 2, 3, 4 nodes and 3 anti-nodes. This is 1, this is 2, and this is 3, okay? So always the number of nodes is one number higher than the number of anti-nodes, okay? And which brings me to the very important point in here, and we still have less than, no, we actually have more than 10 minutes. So the Doppler effect again involves a source, involves an observer, and involves a wave itself. So there are 3 element players, and all of them, they could have potentially velocities. So the source could be moving with its own velocity of source. The observer could be potentially moving with his own velocity, and the wave has its own velocity. So everybody can move. But one of the ways to think about it is to keep the observer stationary and think about the source. Is the source coming toward the observer or moving away from the observer? If the source is coming toward the observer, the frequency is higher. If the observer is moving away from the observer, then in this case, the frequency is lower, That's typically. If there is no change in frequency, that means they are stationary or they're moving with the same speed with one another, relative to one another. Okay. So here is the case. I have observer A and observer B, and I have a source in here producing a hum frequency. Okay. If none of them is moving, then in this case, both A and B will hear the same frequency, because I'm assuming that it doesn't matter. Okay. The intensity matters in terms of distance. So, but the frequency doesn't matter in terms of distance. But just for the sake of argument, I'm going to assume that both A and B are in the same distance from the center, which means that they will also hear the same intensity. Now, when the source is moving one way, to the right, for example, then B in this case will see the wave fronts getting closer and closer from one another. So in this case, the wavelengths are less and less, which means the frequencies are higher and higher. Remember, the frequency and the wavelengths are against one another. Here is how the speed is. The wave speed is equal to the frequency times the wavelength. Since the speed of the wave, as far as you're concerned, sound doesn't change, so it's moving with the same speed. Because the distance between each and every one of the wave fronts is getting smaller and smaller, so in this case, the pitch, the frequency is getting higher and higher, since this one is getting less and less. For this scenario, it's the opposite. The distance between consecutive wavefronts, consecutive crest and crest, if you like, or consecutive trough and trough, are getting less and less, rarifications and compressions. Then in this case, this distance is getting higher and higher. Actually, the distance, the wavelengths are getting higher and higher. Since the wavelength is now getting higher and higher, the frequency has to go down and down so that their product will stay the same. So that's basically, in a nutshell, what the Doppler effect is. Okay. If we did the argument backward, if we kept the source stationary and then forced B to move toward the source and A to move away from the same source, the same thing. So whether or not the source is moving toward the observer or the observer is moving toward the source, this is both of them are approaching one another. If the source is moving away from the observer or if the observer moving away from the source, both of them are receding from one another. So the same results would work. This is basically, you have experienced probably this one firsthand. Okay, I know we have about 5 minutes, a little more than 5 minutes. So, which brings me to the last point of the discussion today. The Doppler effect occurs for, of course, it occurs for sound, it occurs for light, it occurs for everything else. But one of the main applications for it is the redshift that is seen in the universe. This is why we know the universe is expanding. If somebody asks you why, it's because the light coming from the different galaxies, faraway galaxies, appear to be redder than what it should be. Okay. For example, you know specifically what the color of the hydrogen atom when it's excited is going to be. You know how much value it is. But instead of it's that value, it's getting closer to the red. It's not necessarily red, but it's moving toward the red. That's why it's called the redshift. Okay. So here is that frequency. It's supposed to be here. Okay. Here is where the red color is. Here is where the blue color is. You measure it for a specific star, I mean, a specific galaxy, they have to be very far away. You find it here instead. This is the shift we're talking about. The bigger the shift, the faster the star is moving. The faster the galaxy is moving. So that's another point of the discussion today. The reason why we know the universe is expanding is because of the Doppler effect when we measure this for the faraway galaxies. You want me to put it in words for you guys?
Yes, please. Yes.
Okay. Universe is expanding because we noticed.
I also read that as the universe is expanding, Earth is actually being pulled closer to the sun.
I'm not sure about that, honestly.
That's what I read.
I'm not sure if that makes sense. Yeah. I'd like to see the source. Okay.
Well,
Actually,
I'll find it and I will give it to you.
okay. Okay. The universe is expanding because we noticed that light of far galaxies shifts towards red, which means that it's going toward lower frequencies. Lower frequencies. That means that they are moving away, okay? Meaning that they're receding from us. Receding. Did I spell receding correctly? I don't know. From us. Probably I'm missing another E somewhere, okay? Okay, let me check on this thing in here. I don't want you guys to type something and then somebody else will read it and say, oh man, physical science one, they don't know.
It looks right.
Okay, yeah,
Yeah.
that's correct. Okay, I don't want somebody else to comment on our spelling skills, okay, although we're not doing English here. So that's good. Okay, so we did good. Okay, I'm glad
This is not an English class.
Okay, so the sonic boom, and that's where we're going to close the topic on it, is I mentioned it already. So when the source is moving with the same speed of the wave, then in this case, there is an accumulation of wave fronts, as you can clearly see in here. The person who's sitting in here and observing this will not hear anything until this part of the cone, which is called the cone in this case that forms, hits his ear or her ears. And that is a big intensity because there are so many wave fronts that are sitting on there. So actually they will hear a far more intense sound than they would otherwise, and they will hear it like a boom, like an explosion. That's why it's called a sonic boom. And I mentioned again, if it's the velocity of the source, in this case, is less than that of the wave, there is nothing. You will have sound probably, like I said, shifted with Doppler effect, but that's fine. But then if you are right at the wave, in this case, all of them, they accumulate. This is a so-called wave barrier. In this case, the cone is forms. And of course, it's moving away, then there is less and less accumulation of waves in here, okay? So this is in a nutshell your chapter. We still have about 3 minutes. Let's talk about the musical sounds again.
I'm sorry, can you go over the 3 questions? I just want to make sure I have everything.
Do we have 3 questions or more?
Is there 4?
We have one. We have one. Okay. There was another question that has to do with the frequency.
I got Law of Reflections is 3.
Yeah.
3? Yeah, there was another one for this one. Wasn't it this one also?
You want this one, the universe is expanding?
Sure.
No, this one. The frequency when we have 20 hertz is 1/20th of a second. Are you guys watching what I'm showing or not? Are you looking at the PowerPoints?
Yeah. That one
I am.
That one should be number 2 then? The 20 hertz?
Yeah, the 20 hertz, the conversion, because I want you to really be familiar of how to make conversions. And there was, what is the other one? You guys remember it?
For question number 3?
Yes.
I thought that was the Law of Reflections.
Yeah, that one's, the one for reflections of angle.
Yes, the law of reflection, that's important. The angle of incidence is equal to the angle of reflection. And the 4th one is this one. So we have quite a few today.
Yeah, and I'm confused on which is what. So how do we go back and find the answers?
Okay. The answers are actually in the recording. That should be your... Okay,
Yikes.
the first question. Okay, first question. The difference between, and you can write it down if you like, okay, the difference between a wave and a vibration is that the wave travels in space, whereas the vibration only in time, okay?
Are you going to write this down for us? It's a lot, Cher. I can't write as fast as you're talking.
Okay, the difference between a wave and a vibration, is the wave travels in space in addition to temporal, or however you want to put it, okay? I'm putting it in my own words, so you might choose a better word for it. Temporal behavior, meaning behavior in time, okay? Okay, that's one thing. So that's my own words. You might choose your own words for it.
Okay, what is temporal behavior? What does that mean, temporal?
Behavior in time. That means it changes with time. Changes.
I know what a temporal lobe of the brain is, but I don't know what temporal behavior is.
Okay, so let's ignore that thing in there. Use your own words, okay?
Okay.
So that's it behaves with time. Okay, so it changes with time. Okay, so that's what's one question. The second question has to do with the frequency that I already mentioned. If you want to type that, or you're good with that?
But what was the actual question to that one?
The question was, you have a 20 hertz frequency. How much is it that in period? That's a slide in there. Did you find it?
No. I don't know how to go back to the slides, actually.
You don't have the slides? They should be on Canvas, don't they?
They are right. Oh, okay, gotcha.
Okay, so this is the question.
So do you want that as the actual question, like if the frequency of a particular
I want
wave?
you to be familiar with how the frequency and the period are related to one another. By the way, we ended the class. This class should be ending at 9:55, and we are 9:55. Just for the people who would want to leave. So that's the question. Okay? Yes.
They don't want to leave. They want to hear this. Super important.
Okay. So how the frequency and the period are related to one another. Okay. So in this example, you have 20 hertz. And it's 1/20th of a second. So I want you to relate the two concepts to one another. Okay? Yes?
Okay.
That's slide number 12. Okay?
Okay.
Make a note of it.
Okay, got it.
Okay, and then we talked about the reflection. The law of reflection says that the angle of incidence is equal to the angle of reflection. You want me to write that one too?
Yes, please.
The law of reflection states that the angle of incidence is equal to the angle of reflection. Sometimes. Okay. What was the third one? The last one is I gave you that. Okay. The universe is expanding because we noticed that. Okay. They're in good shape?
I think so.
Okay. The last part has to do with the musical instruments and basically the fact the difference between a tone, which is just a normal frequency, I mean, like a repeating sound versus a non-noise, which is random frequencies. Okay. So this is in a nutshell. You will have chapter, again, I lost track of the numbers. This is chapter 10. You will have chapter 11, hopefully by the end of the day. You will also have a homework assignment for you guys. And you will also have a quiz at the end of this week. Okay?
It's a lot of stuff.
See you guys next Thursday. This coming Thursday, I should say. And have a good rest of the day.
Thank you.
Thank you.
Okay, bye.
Thank you.
Bye.